wanted to thank you for joining the next to last talk at KubeCon. So today we're going to talk about securing data applications at Pinterest with finer grain access control on Kubernetes. I'm Soam, and I'm joined by my partner in crime, Will. We're both at Pinterest Data Engineering. And we've worked on, I guess, the intersection of big data, data privacy, and ML for quite a while. And so we're just going to talk about how we built this very large-scale, next-gen big data platform and how we resolve some of these security data access issues. Okay, so our talk is divided into 4 parts. The first part, we're going to give you a little bit of the landscape of data at Pinterest. So talk a little bit about the data platform, talk about Mocha, which is our Spark on EKS based batch processing system, and then shift on to some of the finer grained access control concepts. And then I'll hand it over to Will to talk about more about the implementation of finer grained access control, or FGAC that we call for short. And then we'll have some conclusions and next steps. So Pinterest, if you think about it, one way of thinking of Pinterest is it's a very large ML-based recommendation engine. Users deal with pins and boards, and Pinterest will make recommendations based on their activities. So what you're seeing here is a very data-centric view of how Pinterest collects data and processes and makes it available, right? So you have apps, browsers, kind of starting at the top, you have user activities, and then there's a API service running at the back end, right? Very large scale, collecting user activity information. There's also third-party data, like say merchant catalogs, stuff like that. And then it further flows downstream. It's picked up by, say, either our change capture system, CDC, or Apache Kafka, from which it can either go directly into S3, or it'll go into our big data platform. So there are 2 parts. There's the streaming part, and then there is the batch processing part. We'll focus more on the batch processing this time around, but a lot of the conclusions and the techniques we use will apply to streaming as well. And then the output of all of this would be recommendations, cleansing data for data warehouse, models, and signals. So zooming in even further, so this is Mocha, our batch processing platform at Pinterest. So we're in the middle of or almost maybe towards the end of a transition from our previous batch processing platform, which was Hadoop-based, to Spark on EKS. And by the way, through the purpose of this talk, we'll kind of interchange Kubernetes and EKS. We use AWS services within that a fair amount, and that'll feature more as we kind of go forward. So here, what you'll see is users will compose jobs, say using Airflow, or they'll submit interactive jobs via Jupyter or Querybook, and then underneath the covers, we'll decide whether to send it to Hadoop or to Mocha. By and large, these days, it's mostly Mocha at this time. So why did we do the move? There are the usual reasons. We were consolidating compute frameworks. Cost efficiency was a factor. We wanted to future-proof against Hadoop. It was getting old. People are moving on to other things. But the biggest reason for us was security and containerization, what's provided by Kubernetes, amongst others. A lot of the Hadoop security controls are flaky, tough to maintain, like Kerberos, KDC, so on and so forth. And we really wanted to leverage all the security controls that come with Kubernetes. Also, AWS has built-in services into EKS that we wanted to leverage. For example, identity services. And then finally, we have built Pinterest infrastructure internally. There are internal services for providing security that we wanted to leverage. A quick kind of painting of where we are in terms of Mocha. We have about 12,000 EKS nodes, about 30K Spark jobs per day. In S3, we manage around an exabyte of data, about 80 petabytes of data processed daily. The cluster size we're still working on. That could be a whole separate talk. about scalability issues with Spark and EKS. And then, not pictured here, but we run at peak, about 350K pods daily, at peak, right, during the day. And by the way, this is only EKS, and Spark doesn't include the Hadoop numbers. And for fine-grained access control, we have a bunch of these running in that, but not all. Okay, so here's the architecture of Mocha in general. You'll see it's a fairly complex collection of systems and services, all kind of surrounding the EKS clusters, right? So on the left, you'll see ways in which users can submit jobs into Mocha. So there is Jupyter, there's Querybook, which are mainly used for dev use cases, for interactive jobs. And then users can write their own DAGs using Airflow, which then make their way downstream. So let's walk through what that looks like. So Airflow jobs and then interactive jobs come through Livy, and they make their way to Archer. So Archer is kind of the key for us. Archer is a job submission gateway into EKS. And what it does is it'll create a Spark application CRD and submit that to the correct EKS cluster, which it will select. So within the EKS cluster, we have the Spark operator running, which is a CNCF project. And what that will do is it'll take the CRD, translate that into the right kind of Spark pod, driver pod, which will then talk to Unicorn, which is another, or rather Apache Unicorn, I should say. And that will take the resource requests, assign the right queue. And Unicorn, by the way, is open source batch scheduler for Kubernetes that we use extensively. And Unicorn will then actually assign the right resources, find the right queue, and then get the job running. So once the job runs in the various set of pods, it's going to consume data from S3 and also shuffle data using Apache Kelleborn. And then finally, at the end, it's going to push the data back out to S3. So that's a very quick run-through of Mocha. We'll now transition into talking a little bit more about the concepts behind finer-grained access control that we wanted to incorporate into Mocha and why we wanted to do that. So the reason we wanted to do that is there are bunches of data sets at Pinterest, right? But we don't want everyone to have access to all these data sets. So we want to differentiate so that what Will may have access to is not something that maybe I would have access to, and vice versa. So the primary concept we started off with is every user and workload would have an identity. And these identities would be authorized to access resources. Identity 1 may have access to a certain set of resources, in which, in our case, these are S3 datasets. Identity 2 may have access to a different set of resources. That's kind of the idea behind this diagram. So kind of building on that further, workflows, users have identities associated with them. And then we map these identities to access policies. And so Will may have access to a certain set of access policies. I will be mapped to a different set of access policies. Maybe we might have some in common. And then we would take these access policies per user and then map that into the right access credentials. So this is kind of the basic concept behind our system, which is users and workloads identities are passed securely onto Archer. So the way we do this is from the clients on the user side, we securely transmit the identity using MTLS and certificates. And then when Archer gets it, it will take the user identity and it'll inject pod annotations into this workload, into, say, the Spark CRD, or maybe the Flink CRD, or the Ray CRD. Once the actual job is running, when it, say, tries to access an AWS service, in our case, S3, it'll use the AWS SDK. Now, within the SDK, it's configured, or will end up using a credential provider that actually accesses the AWS metadata service that's running on the EC2 host. So that's the AWS IMDS service. Now, within EKS, the standard pathway is actually not this, right? For users, there is URSA, there is OIDC, stuff like that. We actually opted to bypass that and use an approach where it tries to go directly to the IMDS, which is the host level, EC2 host level metadata service. But what we do is, it doesn't necessarily make it all the way to the local IMDS, we intercept it. We have a identity access management proxy at Pinterest system. So it intercepts that call, and then we route it internally to our own credential vending service. And so within the credential vending service, we now have access to what the identity is of the request that's being made. And we maintain the policy mappings. And so we'll use that to generate a credential, really an STS token. So STS is AWS's security token service. So it's a temporary STS token that goes back all the way to the user or the workflow that requested that access to S3. And it's a customized STS token. And then it now has the ability to access the S3 bucket. Okay, so that hopefully gives an idea of what the basic concept is behind access. I'll now transition to Will to talk more about the various components.
Cool. Great. Now that we've covered the basic concepts, let's take a deeper dive into the components that powers fine-grained access control for the platform. First, let's do a quick background on the standard credentials provider that provides credentials from an IAM role attached to an instance profile. So first, a request from the client goes to the on-host instance metadata service. This calls AWS to fetch credentials, which IMDS returns back to the client. This means that all clients of the host share the same credentials, which doesn't work well when running a multi-tenant or operating a multi-tenant platform, especially where on that platform, each tenant may have varying levels of data access. So instead, what we want to do is be able to vend credentials on a per pod basis. And one thing you'll notice in this diagram is that we include IP tables. You'll see why shortly. Cool, so let's go through the flow for a fine-grained access control enabled client. So requests begin the fine-grained access control lifecycle at the credentials provider. For us, a majority of requests go through the S3 file system library, which is configured for us to be using the instance profile credentials provider. But this will actually work for any standard AWS library. So instead of the request going directly to IMDS like the standard way we just talked about 2 slides ago, the credentials are provided by the instance profile, where the credentials are provided by the instance profile. The request here is instead rerouted via IP tables to Drome. And Drome here is a lightweight security process which runs as a daemon set on Pinterest Kubernetes clusters. So Drome fetches the metadata for all pods on the host via the local kubelets pod endpoint and determines if the requester is coming from a Kubernetes pod. If the requester isn't running on Kubernetes, Drome will simply forward the request to IMDS, like the normal instance profile-based credential approach. However, if Drome, the pod is running on Kubernetes, Drome will check its own local credentials cache for an entry matching the pod's metadata. And if there is a match, it'll just return the cache credentials back to the user. If it's a miss, Drome will pass the request to Valance via MTLS with the associated pod metadata. Valance here on the right-hand side is a centralized security service which authenticates with Drome and fetches credentials from either AWS or our internal credential vending service, which we will also get back to shortly. Valance maintains a cache of running pods on all EKS clusters. And so when a request from Drome comes in, Valance validates the originating pod's metadata with either its cache or the Kubernetes control plane. Valance will then reach out to AWS or our internal credentials vending service, again, which we will get back to shortly, before returning the response back through the chain. Great, so now that we've covered all the components, let's go through the entire fine-grained access control request flow. So to recap, first, the client using a standard AWS library makes a request for credentials to the IMDS. This request is rerouted to Drome via IP tables. Drome will then query the kubelet to confirm the request is coming from a Kubernetes pod and fetch the corresponding pod metadata. If the cache has matched metadata, it'll return the cache credentials back to the client. Otherwise, Drome makes an MTLS request to Valance with the associated pod metadata. Valance will confirm the request, or will confirm whether or not the request is in its cache. If an entry is present, it'll just return that back to the user. Otherwise, it'll query the Kubernetes control plane. And depending on the annotations on the pod, Valance will fetch credentials from AWS directly or through the credential vending service. Great, so now that we've covered the end-to-end fine-grained access control flow and most of the main components, we can talk quickly about why Drome and Valance are necessary. So Drome runs as a lightweight daemon set, which only needs to handle queries for pods or processes running on the same node. Whereas Valance, on the other hand, is a centralized security service that handles Drome requests from all EKS clusters. So utilizing both Drome and Valance, we are able to transparently intercept requests from native AWS providers and inject our own custom credentials that aren't tied to an instance profile. Because this is compatible with the standard AWS SDK, it's not tied to any specific application logic, which also means there's no security-specific logic within the application, which simplifies and hardens the security model for any application running on Kubernetes within Pinterest. Great, so we skipped over this earlier, but now we can go back to the credential vending service, which we touched on in a previous diagram. So the credential vending service, or CVS for short, is a data privacy service which maps Pinterest LDAP users to permissions in AWS and STS tokens. So CVS takes in authenticated requests and looks up the LDAP group for the requester. The LDAP group in this case can either be a human employee or a service account representing a service or workload. CVS maintains a mapping from LDAP groups to S3 policies. So what CVS does when it receives a request is it initiates an assume role request with AWS, and it passes in two key values. The first is the role ARN. This is the static IAM role, which actually has admin-level privileges or admin-like privileges to all of Pinterest S3 data. The second is a policy ARN. This is a session policy for the group. So the results of these two is a scope down role equivalent to the intersection of the admin IAM role with the union of all the IAM policies. And as a safeguard, so we don't accidentally vend the admin-like privileges to any client, CVS requires that there be at least one valid session policy present. And then these scope short-term duration credentials are then passed back to the user. So in order to get this working on Kubernetes, we actually utilize two key Kubernetes constructs to enable fine-grained access control. The first is annotations, and the second is a service account with a scope-down RBAC policy. So when Archer receives a request for a job with FGAC, or fine-grained access control, enabled, it sets several key annotations on the application, which are then passed down to the pods. So the first is the FGAC ENV, or the environment. This is the environment that the pod is running in, and it's used for, or used to determine which CVS backend we're going to hit. The second is the requesting user. The third is a fine-grained access control SPIFFE ID for the pod, which uniquely represents a workload within the platform. It is actually associated with an X509 certificate within the pod. And so the SAN of the X509 certificate is actually the SPIFFE ID set here. And then the fourth is an IAM role. This is mostly here for legacy purposes. In the FGAC world, we're not really using URSA or any IAM role related policies. But for FGAC, we use an IAM role with no policy attachments. And we run all FGAC workloads using surface accounts that don't have any URSA annotations. And we scope down the RBAC policies as much as possible for the service account type. And so if you notice here at the bottom, we have the, RBAC policy, which is part of like the standard Spark operator. But here we scope it down quite a bit from what's available in the open source. And so lastly, we wanted to talk about application support. So this slide is actually kind of a gotcha because with how we've implemented fine-grained access control, there is no application-specific logic required. At Pinterest, we currently have fine-grained access control enabled for a large portion of Spark and Flink applications. And for next steps in the short term, we're looking to onboard all Spark and Flink to fine-grained access control and incrementally roll out support for Ray and PyTorch applications. And then longer term, we're looking to support columnar fine-grained access control to restrict access to columns in datasets that have mixed data sensitivity. Great, so in conclusion, with fine-grained access control, we ensure that all workloads have an identity at the pod level. All data access uses temporary credentials with scoped access. We ensure compatibility with pretty much all standard AWS libraries. And there is no workload-specific implementation required from the user. Great, so that concludes our talk. Here's a QR code to the session where you can download our slides and also leave feedback for us. Thanks all for coming.
Yeah, thank you for coming. Okay. Not too bad.
Hi.
Hey.
So the AWS implementation is very IMDS specific, right, on AWS. How might you do this if you were on-prem or another cloud? What would be like the
So I think got it. So you're asking if we were, so there are certain things, right, that are tied to AWS. Specifically, this notion of intercepting calls to IMDS, and then the actual vending of the credentials itself, the STS token. Those would be the points. If we wanted to move to another cloud, for example, or try something else, those would be the areas we would want to change. So those are the main dependencies.
Okay, thanks. And then the second part is like, where do they set, is it dynamically figuring out what per policies to scope down to, or do they set the policies for the job in another place and then CVS grabs that policies depending on the user? Like where do they declare what exact policies they need, or is that dynamically figured out?
So if you look here, the light blue box, the LDAP group to policy mapping, this is actually a set of pastis policies. So the mapping itself is checked into the code. So it requires code review from another engineer. So it's kind of like a static mapping in a sense. And these mappings go between, say, like service accounts, production service accounts, to all these different policies that we have.
So the TLDR is, there is a review process by which this stuff is added or removed.
You said every pod has a X509 cert. What's adding that, and what are you using that cert for if you're using the pod's metadata to basically store the delegated identity anyways?
We have, it's not in this diagram, but we have another security service which runs on every host within Pinterest called Normandy. And so this is able to issue certificates. Well, it previously issued the certificates just for the host it ran on. But now that we have support for like sub-host identity, it's able to issue certificates.
At the pod level.
Yeah, at the pod level. So the other reason why we have these certificates within the pod is for like service-to-service communication.
Yeah.
So that's like, you're basically, one of the things with FGAC is like, you can't just have FGAC in one part of the system. Every interconnected component also needs to support this identity-based like access policy. And so for us, these certificates are mostly used for service-to-service communication.
Cool, thanks.
Yep.
So you said, so this works for both users as well as jobs as identities?
That's right,
So how does the LDAP group mapping look for like non-human users? Is it like a generic service ID or something?
You were asking about like for production service accounts, like production workflow or something like that?
Yeah.
No, I think the distinction between how we handle usernames versus workflow names.
Yeah.
So they all have existence in We create entries for both in LDAP. Users we have already, right? If you're on Pinterest, right? If you're employed Pinterest, you'll have an LDAP entry. For the workflow stuff, we'll have to add that, right? But we have to ensure, and that's part of an automated process for workflows. So that, say, when you're writing your DAG, you will put in your workflow name as part of the DAG config, and then it goes through a review process to make sure that you are who you say you are.
I'm wondering, have you considered other open source tools to replace this? Because like with Istio, you get MTLs for free, and you get Spiffy IDs for free, right? So you can do that. And then also for user authentication, like you can just pass around a JOT, which contains like the user's, scopes and that. So have you considered those options?
I think it's fair to say there are multiple ways of attacking this. I think, in the previous talk from Uber, we saw a way of using Envoy, right, as a way of assigning service IDs. So I think what works for us is simply that it's largely transparent to the user. If you recall in the previous conversation, the Uber team had a lot of trouble getting people to use that system. Right, so I think what we wanted to do was something that was as transparent as possible. And so the real entry point for users is as long as they use the AWS SDK, which they have to do, right, to access the AWS services, this provides us with a clean way of intercepting and assigning the right tokens. That was the main rationale.